Hi, my name is Bob Stern. I'm the principal metrologist here at Keysight Technologies. Today I'd like to talk to you about what we're able to do in standards lab calibrations at our El Segundo Center of Excellence. First thing you see is a locked door. What it means is that we understand that temperature stability is very important. When you go inside, you're going to see a thermometer with the current reference value. In order for these measurements to be valid, it has to be at 20 degrees Celsius plus or minus a half a degree. Next thing we need to know is what are our reference gauge blocks. What you're looking at is the reference set that was calibrated by NIST. This is as accurate as any calibration lab can have. The way we take advantage of these reference blocks is you then go to the actual measurements. You have a gauge block comparator. So first you put in the reference one that you know the actual value, then you zero the gauge block comparator, and then you put in the one that a customer submitted. And the difference that you see on the reading, that's the error between the two. You can see that our technician is wearing a coat, wearing gloves, and there's even a plastic shield to shield her breath from the item that we're measuring. All of this is done to ensure that when your gauge blocks are measured, that temperature effects are absolutely kept to a minimum. Now I'd like to turn our attention to torque. Torque is the cross product of the length times the force. And it's expressed in Newton meters in SI units, but in the English system it can also be pound inches or pound feet. Once you can accurately measure mass and therefore force, and you measure length, you're in a position to calibrate devices which can measure torque. So let's take a look at how they make temperature measurements at our El Segundo Center of Excellence. This is the temperatures of several fixed point cells. These are actually primary standards. And this is one of our technicians putting in the triple point cell for water into the temperature bath. When you have the triple point, you have physical properties and you have an extremely accurate implementation of temperature. These are the cells which go into the temperature baths for tin and zinc. The very most accurate thermometers are platinum resistance thermometers, where you measure the resistance and then using the international ITS 90 tables, you're able to convert that to temperature. As we look at a sample reference thermometer from Fluke or Hart Scientific, you're seeing that the expanded uncertainty from the manufacturer is as small as 0.012 degrees C. So it's highly accurate, very low uncertainty. With these temperature primary standards that we have, we are able to measure down to as small as 2.3 millikelvin degrees, or in other cases even smaller than that. So we're talking about very, very good accuracy, very low measurement uncertainty. So when you send in a PRT or an SPRT to us, we use these primary standards and we're measuring directly against that. Of course, from time to time we do a measurement assurance program with NIST where we send one of our SPRTs to them and compare the results of our primary standard with the national primary standards. Over a wider range of measurements, many people use thermocouples. This is our thermocouple test system. This is able to generate precision temperatures up to 1,000 degrees Celsius. The measurement uncertainty, it's very, very good. But if you have thermocouples that you wish to have calibrated very precisely, the El Segundo lab is an excellent location to do that for you. Now I'd like to turn our attention to vacuum measurements. This is the vacuum chamber that was built by one of our folks in El Segundo, Glenn Gaza, for measuring ionization gauges. Over the range of 10 to the minus 4 torr to 10 to the minus 7 torr, the uncertainty is well under 10%. So if you have ionization gauges and you would like to have those measured accurately, this may be a capability that we can do for you. Now I'm going to move to optical measurements. First, you're looking at a reference absorption cell. This is essentially a comb filter. So if you put a tunable laser in one end and then put the output into an optical spectrum analyzer, you can measure the wavelength and calibrate that optical spectrum analyzer to incredible accuracy. The expanded uncertainty is 0.0006 nanometers. This is one of the things that NIST does. They create reference materials for the express purpose that calibration labs are able to use those for very, very accurate calibrations. Now let's take a look at another reference material. This one's coming from UKNPL. We have two lengths. I think one of them is 13 kilometers and the other one is 5.6 kilometers. These are for use in calibrating optical time domain reflectometers, or so-called OTDRs. And the idea here is that the distance to the discontinuity, which is the end of the cable, is very accurately known. Therefore, you can use this to calibrate your OTDR. I'd like to now move to electrical and RF microwave measurements. As we look through one of the rooms, here you can see some millimeter wave test station. You would also find horn antennas like these. Let me show you how we use these antennas when you want one of your antennas characterized. You use one of those antennas to transmit and later to receive, and then you use the antenna that your lab would submit. We can make very accurate antenna characterizations here in the El Segundo lab. Before I leave, I'd like to review the key deliverables that you'll receive regardless of which discipline we are operating in, both the calibration report and the calibration certificate. So let's just take a look here at the table. You can see the Keysight Standards Lab calibrations on the right-hand side. The first row, primary lab standards. What distinguishes these from our other calibrations is that we use either a primary standard or one step removed from a primary standard. That's where we get the really good accuracy and the really low measurement uncertainties. Moving down to measurement guard band, if the device you send in has a specification and part of the job is to check and see whether it passed or failed, we will apply an expanded measurement uncertainties guard band. However, if it is an item which requires only a characterization, such as a power sensor when you're looking at the calibration factor, then we simply provide the calibration factor and the uncertainty associated with that. You will receive always both the data that we measured and the measurement uncertainties, and because we are accredited in all of the parameters corresponding to these measurements, you will receive the accreditation body symbol. And then moving down into the standards compliance, the deliverables I've just indicated to you are what it takes to meet ISO 17025, and they also meet both of the Z540 standards, the old -1 and the new .3, as well as easily passing anything that's in ISO 9001. So from a standards compliance standpoint, you're very well covered. If any of the services that I have described look interesting to you, I encourage you to either contact your service representative from Keysight or contact one of our call centers, and we will be glad to look up whether we're able to take care of the device that you have. And if that looks good to you, we'd be happy to make a quotation. Thank you very much for listening.